Course 3, Lesson 51, we are looking at negative exponents and scientific notation for small numbers. Now, we have quite a few exponent rules, and so to really quickly go through them, remember, if we are multiplying together two powers that have the same base, we can add the exponents. If we are multiplying and we have a power to another power, so a number to an exponent, and then that is to an exponent, we actually multiply the two powers. And then a power of a product property, we say if we have two things in parentheses with different bases that are multiplied together, and those are to a power, then each of them gets that power, okay? And we multiply whatever power we have there. So for a couple examples of these, just to make sure that they are clear what these mean. So let's say for the first one, let me just switch the color on my pen. For the first one, let's say we have 5 to the 6th power times 5. Let me start that over. Let's get rid of those lines. Sometimes it just likes to do that pen all over the place. Let's try this again. So if we have 5 to the 6th power, let's try it over here. Oh well, times 5 to the 3rd power, we can, since they have the same base, add those exponents and get 5 to the 9th power. For the next one, a to the m to the n, let's say we have x to the 3rd power, all of that to the 5th power. We multiply those exponents and get x to the 15th. And power of a product, let's say we have x to the 3rd times y to the 6th. All of that to the 4th power, well, we multiply each of those and get x to the 12th times y to the 24th. Remember, that only works if those numbers inside the parentheses are being multiplied. And we have one other typical ones that we've seen before. When we divide with exponents, we subtract. So in our case right here, x to the 3rd divided by x to the 5th, we end up getting x to the negative 2nd. But another way that we could show this is actually keeping our x's where they are. So if we have x times x times x for x to the 3rd, x times x times x times x times x. Well, when we simplify, we can get rid of a bunch of pairs. We are actually left with 1 over x squared. These are actually the same thing, x to the negative 2nd and x squared. These are reciprocals, and when we go from a negative exponent, we can show it as its reciprocal over 1. So this is kind of our rule for that. Our first rule, though, a to the 0 power, anything to the 0 power is 1. And a to the negative 2nd, a to the negative n is the reciprocal of a to the n. So we can say a to the negative n equals 1 over a to the n, okay? I like to think about this, and this is a poor example, but it kind of helps you remember. If this number, a to the negative n, is being bad, we're going to send it to the basement to start thinking about its life choices. Okay, it goes to the basement of our fraction. And if it is in the basement, being bad, we could send it to the attic to rethink its life choices. Okay, so you can think about when we flip it over that fraction bar, we end up getting rid of that negative exponent. And this is why. When we have our pattern here, 10 squared is 100. 10 to the 1st is 10. Well, we actually divide by 10. And to the 0 is 1, so we divide by 10. Once more, we divide by 10, and now we're in fractions. Once more, we divide by 10. Every time we go down an exponent, we're really dividing by that number. And another way to show each of these fractions here is 1 over 10 to the 1st and 1 over 10 squared, which means 10 to the negative 1st is the same as putting that 10 to the now positive 1st power in the denominator, or 10 to the negative 2nd is the same as 1 over 10 squared. Okay, so think about getting rid of those negative exponents, because in math we really don't like to see negative exponents. Now, which of the following does not equal to 10 to the negative 3rd? Well, we would say, what are the different ways that I can show 10 to the negative 3rd? Well, one of the ways is putting it in the denominator and getting 1 over 10 cubed. which is actually 1 over 1,000 or 1/1000th. So the only one that does not work here is negative 1,000. A negative exponent does not actually mean a negative number. It means we're dividing by all of those tens. Find each missing exponent. 10 to the negative second times 10 to the fourth. We add these together and get negative 2 plus 4 is 2. And then here in the second one, we can do it one of two ways. We could subtract because we're dividing and get negative 2 minus a negative 4. And, well, those become positive and we actually get 10 squared. Or you could have thought about it as I'm going to bring this negative exponent to the top. And so that we have 10 to the negative second times 10 to the fourth, which is 10 squared. Let's try some of these examples. 2 to the negative third. I want to get rid of that negative exponent. It's not a negative number, but it is a fraction of 2 to the third, 1 over 2 to the third, which is 1 over 8 or 0.125. Whereas if we have negative 2 to the third, we don't actually have to do anything with the exponent, but we could multiply it out. So negative 2 times negative 2 times negative 2 is negative 8. And then 3 squared times 3 to the negative second, when we add those together to get 3 to the 0 power, which is just 1. And lastly, since there's multiplication in between all of these, I could switch them around and actually say that I have 2 times x to the negative first times x squared times y to the negative second times z. And I can combine like terms and get 2 times x, because x to the negative first plus 2 is just x to the first. And then we have y times y to the negative second, so I have y to the negative first times z. But I still don't like seeing those negative exponents. So I actually move this y to the negative first to the denominator. But only that one needs to move because that's the only one that's been bad and needs to go to the basement. So I end up getting 2xz over y. And that is my final answer. That's what I would look for because I want all of those exponents to be positive. Okay, a couple more here. 3 to the negative second I can show as 1 over 3 squared or 1 over 9. 2 to the negative third is the same as 1 over 2 cubed or 1 over 8. And once again we get 2 to the 0, which is 1. And lastly 5 to the 0 is just 1. So make sure you know all of those properties well. Okay. So arrange from least to greatest and find missing exponents. Least to greatest, well, let's put these all in a similar form. So I have 1/2, 0, 1, 1 over 4, because that's 2 squared, negative 1, and 1/10. So it looks like my negative 1 is the smallest because I don't have any other negative numbers, which means 0 comes next. And then I'm looking at those denominators. I say 1/10 is the smallest out of that, 1/4, 1/2, and then 1. Find the missing exponent. We get 10 to the negative 7th, which we should show as 1 over 10 to the 7th. And 1 over 1 is really just 10 to the 0 power, or 1. All right, so a couple more examples of these a little bit more challenging negative exponent ones. Let's first, in this first one, combine like terms. So we have x to the negative third times x and y squared times y to the negative first. So that I get x to the negative second times, whoa, sorry about that. Sometimes it just wants to do that. Okay, so we have, let me write it over here. Maybe it'll like it better. X to the negative second times y. But we can't leave it like that because we don't like negative exponents. So I'm going to take this, move it to the denominator, and get y over x squared. All right, and then this second one here. Once again, let's look at, let's first move some of these negative exponents. So I want to move my x to the negative second down and my z to the negative first down. So they both become positive exponents now, and I have 6y to the third over 2. Now I have x times x squared times y times z. All of those are now in there. And I can start simplifying and say 6 divided by 2 is 3 on the numerator. And then my x's combine to get x cubed on the denominator. Y to the third minus y to the third over y is just y to the 3 minus 1, so y squared. And then z is left in the denominator as well. All right. So I'll let you stop the video and try these out, going from scientific form to standard form. Remember, our tens tell us how much to move the decimal or to multiply by how many tens. So in this case, I'm going to multiply by 2 tens, move the decimal to the right twice, and get 283.4. Same with B, but we're moving it 5 times to the right and get 490,000. Now when we go to negative exponents, we're going to move it to the left and get 0.78, and move it to the left 6 times and get that really, really small number. Okay, some other examples. Put these in scientific notation. So we always want to put it right after the first digit that is non-zero, and we get 3.469 times 10 to the fourth. Remember, stop the video and try these on your own if you would like. And 1.78 times 10 to the 0, 3.9 times 10 to the negative second. Remember, this is a small number, so we had to move it. If we put 3.9, we would have to move it back twice to get to our original. 7.22, well, we start by putting it right here, and we would have to move it to get to the original 1, 2, 3, 4 times. So you get 7.22 times 10 to the negative fourth, and really big number again, 5.6 times 10 to the ninth. You can look back on our lesson of multiplying in scientific notation, but remember, we multiply the numbers and then multiply the powers. Remember, when we're multiplying powers, we add those exponents. So we get 4.8 times 10 to the 12th. Okay, next one. This is a good one to try out. In 1998, the population of the world was about 5.9 billion. In the same year, the population was 2.7 times 10 to the 7th. What percent of the world's population was the U.S. population? Now, we could try and put these in standard form, but that's not going to help us all that much. So let's put them both in scientific notation so that my 5.9 billion, let's see, well, we have 5.9 times 10 to the, well, there would be 6 for million, so there's 9 tens for billion. And we want to know what percent. So if I have the part over the whole, that would mean I'm doing the part of the, which is the U.S. population, so 2.7 times 10 to the 7th over my 5.9 times 10 to the 9th. And we divide our numbers, divide our powers, and we end up getting 4.576 times 10 to the negative 6. It's a really, really small percentage of the world's population. Just a couple more examples. You can write this in scientific notation. Remember, I'm going to put the decimal point here, so to get it to the original, I have to move it back 1, 2, 3, 4, 5, and 6. So we have 7 times 10 to the negative 6th. And if I compare 1 times 10 to the negative 6, that's like taking 1 and moving back 1, 2, 3, 4, 5, 6. Now, that may seem like a really small number, but in comparison with negative 10, this one is actually a whole lot bigger than negative 10 because we're still in the positive numbers. And write 10 to the negative 4th as a decimal number. Well, that is 1 over 10 to the 4th, or 1 over 1,000, which is 0.1000. Let's see, did I get all the zeros that I need? 10th, 100th, 1000th, yep. Okay. All right, I'll leave these for you to try out on your own. Okay. You can try that out. And let me see. I think that's all I want to look at for today. So I hope this is helpful for your homework and for studying.